Hello. My name is Francis Duranceau, and I'm the lead field engineer in the Americas. Today, I want to talk about one of the features that is coming later this year. It's not ready yet. There's still a lot of work to do, but it's a great feature, and the reason why we talk about it now is because we want to make sure that you understand the intentions behind the system. We want to set the proper expectations. As I said, it's not finished. So by the time the system goes out, it will likely change. But it gives you a good idea of what it's going to be. I will start. For those of you who are not necessarily really familiar with jobs, we'll quickly go over what are job systems for. And then I will start covering some of the changes that we had to do under the hood in Unity. And then finally, we talk about the new job system. And instead of being an AI example, I'll show you an example with actually many, many more units moving on screen in parallel. And we will still talk a little bit about the AI example. So the main reason to use a job system is because modern hardware often has multiple cores, and we want to make sure that we use all of them. So a job basically is going to manipulate a set of data. If you have multiple cores, you will have to be careful, not for all the different cores to manipulate the exact same set of data at the same time. So when you're going to plan your job, you will have to really think on your data structure. And I really want to put emphasis here because 95% of the work is your data layout, how you will structure your data, and then jobifying everything will be easy. And the truth is, if you also structure your layout so it's performant with multiple threads, it will also, in most cases, be more efficient in single-thread environment. But not everything can be turned into a job. Often I hear when I go and visit some of our customers in the US, they say, oh, we need a job system, then everything is going to be much faster. Yes and no. Unity under the hood is already heavily multi-threaded. And for what's left, your game, often it's only, well, not everything can be multi-threaded, even in your game. Because some algorithms may have dependencies that do not make it easy to split the algorithms over multiple threads. And but it's also true that some examples are easier to split. Those that are repetitives or where the data is completely independent. And we'll look at one of the examples at the end of the presentation. We'll look at a flocking example where you have multiple fishes swimming all together. One challenge when it comes to job system is to make sure that everything is synchronized. There's a very simple solution that Unity will offer, and it's called, we're using fences or barrier. Basically, we won't start a job until the previous one has finished. So we still have some sort of dependency system here that we can use. The idea is our main thread will schedule many, many jobs, and we will only continue and move forward when all of them will be finished. How do we do that? We wait for the fence that is going to let us know when all the jobs are finished. And when the fence is cleared, we can move on to other jobs. Unity, as I said, internally already is heavily multi-threaded. We have a job system in C++. It drives a lot of our systems. So in 2017, what we want to do is to open that internal job system. And not only open it and make it accessible, but we want to do that in C#. Why? Because in C#, we can also trap a lot of exceptions. Instead of crashing, we just report exceptions. So in terms of iteration time, for you, it's much faster. And it's also less, we want to prevent mistakes as much as possible, and we want to do the hard part for you and just give you the power and the flexibility of the scheduler. When is it going to happen? Currently, we are targeting 2017.2, but it could very well slip to another version later. Well, I think that this image really talks a lot. There's one guy here digging. That's your CPU 0. It would be great to get everyone to work with him, right? That's the intent of the job system. In theory, everything works well. But there are tons of ways where actually it can have a significant impact on everything else in the system. And finally, performance is not necessarily as great as you think it would be. For instance, in this book, I have all the names and phone numbers of the people in America. And this is an example to show you that multi-threading does not necessarily mean that it's going to be faster. And then, on the right side, we took the book, cut every single name with phone numbers one by one. So it looks like a big pile of shredded paper. If I ask you to find the phone number, my phone number, what do you think is going to be faster? If you do a binary search in the book, it's pretty fast. If you have to find 1,000 friends, give them a lot of names, and they look at names one by one, it's probably not going to be faster. So multi-threading will perform well depending on how you structure your data. And in some cases, it's not even worth it. And then you can add a lot more to your data structure by having your data to be sorted or not, for instance. So far, so good? That was the easy part. Well, this example is also very simple, because when you want to multi-thread an algorithm, it's always a compromise that you have to do. It's a trade-off. If I want to build a table, if I'm alone, it's simple. I just build it. But if I want my table quicker, I can also call a couple of my friends, tell them like, you take care of this, you take care of this, you take care of this, and then we get the table faster, but then it means that I may require more tools. I also take time to schedule all of this. My point is, a single-threaded algorithm is very simple. If you go multi-threading, you will need time to organize and distribute your jobs, but it will also cost you memory, more tools, because you will have to copy memory you have to copy memory so the new thread can use memory without having error in accessing the memory from different threads. And even when you think you should multi-thread an algorithm, you also have to consider your hardware. If you target, for instance, the iPhone 5S, it has 2 threads, one for the main thread, one for the rendering. If you add 6 more threads or jobs, you may impact the performance. So it's always important that you look at the profiler before doing the efforts of really transform an algorithm into jobs. Changes that we did inside of Unity. One of the first part of Unity where we want to really apply the job system is for transforms. So we started and made a couple of changes in how we handle transforms under the hood. Now, I think in Unity 5.4 or 5.5, I can't exactly remember, we changed everything, so all the transform under one root element, which is why I highlighted in those red rectangles, they are all packed together under one root. And then we can easily take all the data of those transforms, send that to a different job. Now that you know this, you also understand a couple of issues here. Because if you start to switch one transform and move it from one root node to the other, it may have an impact on performance. Also, if you take the data of your all the transform that is under one of your root node, which we call a transform hierarchy, when the transform change, we currently send a message back to the main thread saying, "Hey, you have to update the transform on the main thread, even though like a job may have changed part of the transforms." So one of the things now that we are doing is, currently it means that we offload everything, but then we have to go back for each single transform that is getting changed. So we're introducing a new system that we call the transform change dispatch. What is it? It's very simple. We will accumulate all the transform change into a big batch and then do them all at once. Very, very fast. This is what we call the transform access. And we'll see later in the code example what it is for. And the fact that we batch all those changes, it can often be done in jobs also. So what is coming in 2017 point when it's going to be ready? Jobs, obviously, but also a couple of new C# attributes. New C# attributes because we want to be able to tell the compiler, this is a job, this is a structure that needs to be needs a different data layout. We want you to really be able to tell the compiler what to do so it does it in an efficient way. We are also adding new types, new intrinsic types, float3. If you're familiar with writing shaders, you'll notice that it's very similar to HSLS. So when you manipulate float3, for instance, you will be able to do swizzling. We are also adding new types, native arrays. It's a structure. The memory layout is really, really tightly packed in memory. And it's available both in C# and C++. And we made sure that there is no marshalling involved. For those of you who were at the talk yesterday about tips and tricks in C#, I was basically saying that when you do marshalling, you literally copy the memory between managed and unmanaged side. Here, those specific types do not need that. Very, very fast. Why does that work? It's because all the memory management is going to be handled on the native side in C++. Which means that when you allocate memory, you will also need to dispose of the memory. Otherwise, you're going to be leaking memory, and the garbage collector is not even aware of that. Why are we adding those new types and the C# attributes? Because we're going to introduce a new compiler. And this is the very interesting part. It's only going to be used for jobs, but we will see the process a little bit later. The new compiler is actually very, very good at optimizing mathematic operations, which will often be the case when you want to manipulate transforms. Here, this is an example of a very, actually probably the simplest job system ever. First, we have a structure of data. We have an array of input data that is read-only. We have an array of output data. And then we have an execute function that takes an index. That execute function is what is going to be called by the different threads to be executed. So here, fairly simple, we simply increment the value on the input data. The execute function is only being applied on one data at a time. But if we look further in the update function where we create our new set of data, then we create the input and output arrays with 100 elements. And you'll see that the native array, I was saying that you allocate, you will have to dispose it, which are the two lines at the bottom, but you also specify a type of allocator here. Is it memory that's going to be allocated for a long time? Is it going to be something that is going to be only allocated for one single frame? We have different allocators for those type of for different type of uses. And then in the middle, there's job data.schedule. First parameter 100, the number of elements that we have in our array. And the second parameter, how many items per job do I want to execute on? So in that specific case, we would have 50 jobs that would call execute twice per job. And then we call the complete function, but we'll get back to this later. Because this basically means we schedule everything, and the complete is going to be blocking until all the jobs are done. So we'll see a different way to use it later. So why is the new compiler so much faster? Because we work on intrinsic types. Those are really tightly packed in memory types. The new compiler knows about vectorization. So it's using a lot like the SIMD instructions. We are also using a lot of the assembly calls that the CPUs are using. And the problem is the VM in C# often doesn't know about all of these assembly calls. And also, finally, we have a trade-off between performance and precision. I don't have it yet in my example, but you'll be able to say things like, I want my job to be really, really fast, and I don't care about precision. What does that mean? It means that if you call a sign function, we may be using a lookup table. If you're doing operations on quaternions, we could be using half floats instead of full floats. You tell us, and then we give you either precision or speed. Where does that new compiler fit in? First, as usual, we have our monocompiler. We take the C#, transform all of that into IL, the intermediate language. Then, for code that is marked as with the different attributes to turn into jobs, we will take the IL and we will convert that into an internal domain model. Basically, a huge graph of all the operations, and then we will optimize on that graph from a mathematic perspective, right? So that's the part where our compiler does the bulk of the work. Then the result will be sent to LLVM. And finally, LLVM gives us executable code, currently in memory, but eventually either in dynamic libraries or static libraries, depending on the platforms that you are targeting. It's also important to understand what the job system is not for. It's not aimed for jobs that are over multiple frames. If you have a complex automated planning algorithm that is taking 20 seconds, and that there's a risk that it doesn't converge, you can't kill the job. Definitely not the type of usage that you should do. Instead, what we recommend is split that algorithms over like smaller cycles, and then frame after frame, offload everything to multiple jobs. So the job system is on a per frame basis. Also, be aware that the job system will be applied on objects like transforms, textures, meshes, and eventually we will probably add even more objects. But it does not mean that the Unity API is thread safe. It's not either to use the .NET API. Actually, if you want to call .NET libraries that are multi-threaded, you better use async or tasks. that are not guaranteed, by the way, to be on different threads. Async and wait are very much like coroutines. You can also call certain .NET libraries that are thread safe. You can call them either from background worker thread or native multi-threading. You cannot use async tasks or native multi-threading to manipulate transforms or meshes. At the moment, if you do that, you'll get an exception. The C# job system is there. It's really for gameplay features. The Unity API, it's not thread safe. So you can't multi-thread that. And finally, people are often using async tasks or native multi-threading for what I would call standalone algorithms. Basically, anything that is not specific to Unity. You could do automated planning using a native multi-threading system. That would be an example. When it comes to best practices, in general, we will put emphasis on having data-oriented design. Usually it means get only the data that you need to work on altogether, no indirections or anything like that. It's usually cache-friendly, more packed in memory. And you could even think about using the analytics services there. So when you boot your game, you know on what type of hardware you're running, and then you could split your different hardware, the hardware into different tiers, and adapt a little bit your strategy here. I said data-oriented design. Design for cache coherency is also very similar. When I say group data physically in memory, once again, it goes back to DOD. And the last line, I say, forget mono-behavior-based designs, but we'll look at how to convert that into a job system. And the truth is, and I said that earlier, if you think about your data-oriented design, it will very likely also get you back performances on single-threaded architectures. So let's look at the 4 steps of converting mono-behavior designs into the multi-thread C# job system. First, I have a very simple script behavior here. This is an exercise that all Unity engineers are going through, where we're getting asked to create a way to get a game object to rotate, the rotator problem. So I have the speed to figure out which speed it's going to turn, and then my update function here. And by the way, this could work for mono behaviors. I'm just using a script behavior because those are the new words that are getting added. But here, what we do is simply change the rotation of the game object in the update function. First step, instead of doing that on a per object basis, let's move the rotation to a component system, where here we have a rotation speed component, which is just the speed, and then we have one component system that has an array of all the transforms and of all the rotators. The reason why I've put the attribute inject tuples is just to make sure that both arrays are in the same order. And then, if we look at the update function, because they are in the same order, we can just do like 1, 4 and go through everything. That is one of our recommendations. As soon as you have more than 5 game objects, you may want to think about starting doing these type of things to improve performance. Then, step 3, we are changing our data into a component data. And the reason for that is just because it's going to be a tightly packed array. It's going to be friendly for the new compiler, simply. And it allows the data to live outside of the game object. When we look at the component system, it's still the same thing so far. And it's the same thing for the update function. The only thing that is left to do is in the last step, we will, here, the update function, or maybe I should go back. Actually, no, OK. So we have the component, iComponent data. So that lives outside of the algorithm. And now we can create a rotator job. We will have to give the time the delta time. Because if you remember, I cannot call the Unity API from different threads. Then we pass the rotators as a parameter. And we schedule the job on the transforms. Let's now look at the rotator job itself. There's the delta time, component data array rotators that we passed as a parameter, and finally the execute function. That's simple. And then suddenly everything is going to be over multiple threads. Let's look at the example that I was talking about. So I'll show you that it's actually not a lie. It works in the editor. Boids, it's basically bird-oid object simulation. So we're going to have, or often we say a flux algorithm, right? Let's go have a look. If I press play, what we'll see is one huge shark that is swimming, and then there are tons of fish that are stuck into a zone, and every single fish is a game object, and this is jobified. If I don't do that, 2,000 transforms, I'm not able to run at 60 FPS. If we look here at the profiler, if I click here, what we can see is that we have the main thread here, we have the render thread, and then we have multiple worker threads that are doing Boids cloud jobs. And then a little bit later, here we have the Boids transforms job. Let's go look at the code. So if we look at the structures that we're using for this, we have the Boid data. Basically, it's a position of one game object and what's the forward direction. Then we have a simulation state that is basically taking a lot of information to do a global simulation. And here, when we look at the simulation settings, what's interesting is that we have, the initialization function, but more than anything else, here, a steering algorithm that is taking the Boid simulation state, a native array of all my transforms, and we have also a hash map that we use to split the environment into multiple cells. So it's easy for every single object to know which one are the neighbors. And here I have my steering algorithm that is going over all my game objects and figuring what is going to be the new forward and position. A lot of math in there. On the other side, what do I have? I have a Boids job. It's taking my simulation settings, my simulation state, an array of all my transforms, the hash map to split the environment. You could think of a binary space algorithm or octree, or all these structures could do it. We decided to use like a hash map into different cells. Finally, and then we have the output for the transforms, and we have the output for the cells. Our execute function, as you can see, is fairly simple. I execute the steer function, and then we adjust all the cells as need be, and then we output the result. So that's one job. Then we have a second job. We have the Boids transform job. Basically, this one is very, very simple, because when you look at the execute function here, all that we do is we take the position and we apply that to a transform, the transform axis. This is the key element. You remember when I was saying the transforms are going to be passed back to a batching system that will write that back to the main thread? This is it. So we have to do that. And a little bit, oops, I opened everything. If I come here at my update function, and then I go at the bottom, what we will see is that we first call the Boids job. We return a fence. When that job is done, we then call the Boids transform job to make sure that all the information goes back to the transforms on the main thread. Which is why at the bottom here, I had the Boids cloud jobs, and then later I have the Boids transform jobs. Here, 512, because I'm going to execute on 512 elements per jobs. Can I try more? What's going to be the difference? At the moment, the Boid cloud is taking about 25 milliseconds, and we're using 6 different threads. So we'll see what's the difference. It still works. It's good. And if I click here, as you can see, because I have so many more objects per jobs, instead of using all 6 worker threads, I'm only using 3 of them. And it's taking about 23.6 milliseconds. Let's put back 512. It's more fluent. We talked about defenses. This is the very interesting part. What would happen if I called the transform job without waiting for the fence? Let's give it a try. I press play, and let's look at the console. I know it's hard to read, but basically it says, the previously scheduled job boid-cloud.boids-job reads from the native array boids-job.cells. You must call job handle.complete. Basically, it's telling you either you have to wait for the job to be completed or you use a fence. If you do multi-threading in C++, usually what will happen? Crash. I have here my unenable. I was saying we do the new array, right? Undisable, well, we also have to dispose. What happens if I comment here the dispose? Once again, in the console, I should get a warning message when we will get out of the simulation saying, hey, you forgot about disposing your memory. You're leaking memory. So it's pretty cool because Unity is doing the hard job for you. And this is the power of doing the simulation in C#. It's safe. Here, a native collection created with allocator.persistent has not been disposed. So, if I come back here, the fact that it's in C# is great, easy to use, safe, and you still get all the flexibility and the power. Still, I was curious and I was thinking, I really like RTSs, real-time strategy games. The first thing that I would have to change is all those pathfinding algorithms. If you're using an A*, you would have to split it. Maybe split it and explore different sections of the A* split over multiple jobs, or multiple layers over multiple frames. You could use a tiling system. You could switch your system for an influence map, or use hierarchical graph. So you just calculate layer per layer instead of doing like a full traversal. And then pathfinding is obviously one good example where you think you can save a lot. But the real AI, taking decisions, is also a very good example. If you use a Blackboard as a knowledge database, everybody, like all your knowledge sources are going to write information on the Blackboard. And then you'll have multiple agents who are going to read from the Blackboard. So all those small algorithms to take decisions on a per unit basis are really easily, you can easily turn that into jobs. But when you think about it, you may want to use fences, have first high-level decision. As a player, what am I going to do? As a non-character player, what am I going to do? Then, when that's complete, I have multiple squads. All those squads could then also become jobs. And finally, when the squads know what they have to do to accomplish the grander plan, you could also have a second fence and a third pass of jobs on a per unit basis. So that's probably a way to change your algorithm. And if you want to do automated planning, just be careful and think that your algorithm must be time sliced per frame. And to make sure that that works, it will have to be fully deterministic. Otherwise, you're still better to use the other different systems out there, like background worker threads or native arrays. But then the problem is you'll have to pass information and marshal data between those threads. So it's really up to you to look at the profiler to figure your best strategy to accomplish those problems. Thank you.